Hi everyone, let's now compute and compare these two conditional probabilities. In part B, what's the probability of an A given a junior? That is, what is the conditional probability that the student is getting an A given that the student is a junior, given that the student honestly tells the tutor that they're a junior. So once we know the student is a junior, what's the updated probability that the student is getting an A? Well, from the formula, the probability of A given junior is equal to the number who are both juniors and getting A's over the number of students who satisfy the condition, here being a junior. On the top, the number of juniors getting A's is 5. On the bottom, the total number of juniors in the class is 14. So the probability, the updated probability that the student is getting an A, given that the student is a junior, is 5 over 14, or about 36%. So if you look at the Venn diagram here, there are 26 students total in the class, but once we know that the student is a junior, then we don't care about all this stuff out here. I don't want to say they're junk, but we don't care about any of the students out here, okay? We only care about the students who are juniors. So we're aiming our dart at this region over here. We're aiming our dart at this region over here. If we aim our dart at this region over here, what is the probability that we're going to get in this overlap, this intersection, the 5 students who are juniors and getting A's? So once we're restricted to this new world of 14 juniors, what's the probability that we'll also get a student who's getting an A? It's 5 over 14. The 26 is irrelevant. And it's a bit more than a third. If we aim at the purple oval here, the probability we'll get inside the brown orange area in here is 5 over 14, about a third. Now, what about the probability of junior given A? Imagine that the student tells the tutor, hey, I'm getting an A in the class. What is the conditional probability that the student is then a junior? All right, well, the numerator is going to be the same, the number of students getting A's and who are juniors. The overlap intersection event, A and junior, is the same as the overlap intersection event, junior and A. B and A and B represent the same intersection event, the same overlap. In both cases, the number of juniors getting A's, that's 5. So the numerators are going to be the same for both here and up here, the 5 up here. But the denominators are different. The number of students getting A's is only 8. We had 14 juniors up here, and it was less likely that we'd have both a junior and an A student. But over here, we have fewer A's, fewer A students. And it turns out the probability of getting both will be higher. We have only 8 A students. 5 over 8 is about 63%. Notice that's very different from up here. So observe that the probability of A given junior, is that equal to the probability of junior given A? No, in fact, they're pretty far apart in this example. Now, let's look at the Venn diagram for C. Now, for C, we restricted ourselves to the world of 8 A students. So we're aiming our dart at this green region over here. The probability that we hit this brown-orange region in here, this overlap region, is 5 over 8. So it was much more likely, in fact, we had a greater than 50% chance that we would hit the overlap region given we were in the green disk. This was much more likely than if we were guaranteed to just be in the purple oval over here. It was less likely. It was about, 35, 36%. There's only about a 35 or 36% chance that we'd land in this brown-orange overlap over here. So if you wanted to be a junior getting an A, the key thing is, are you getting an A? And then it's a lot more likely that you're a junior. Whereas if you're just a junior, it's not that likely you're getting an A. And you can also get that from the tables. Again, we use the 5 here on the tops for both formulas, the number of students in the intersection event, the overlap, but we have different denominators. Here we use the marginal, the row total of 14 for juniors. Here we use the column total, the 8 A students for the denominator. We had a smaller denominator here, so that ended up raising the probability. Now, notice again that these two probabilities, these two conditionals, are very different from each other. People often mistakenly believe that these have to be equal to each other, and that's referred to as the confusion of the inverse. People often incorrectly assume that the probability of B given A must be equal to, or even close to, the probability of A given B. But as we've seen in the previous example, they don't have to be equal, or even close. They could be pretty far apart. Here, the probability of A given junior was about 36%, whereas the probability of junior given A was about 63%. These were very different probabilities. In the next example, we're going to discuss this issue of confusion of the inverse, and by the end of that example, you're going to be better than many medical doctors. Next time.